welcome to today's session of Industrial Electronics and 6. I'm C. Tobejane, and in today's session, we'll be looking at a resistive inductive circuit calculation. I want to believe that you've already studied enough and understood what is meant by an RC circuit, its characteristic curves, its operating principle, and its circuitry, alongside its application. Today, we'll be looking at example 1.8 extracted from the TVET First textbook by Macmillan and Chopin Publishers. The question reads as follows. A series RL circuit consists of a 3 ohm resistor in series with a 1.5 Henry inductance. If a step voltage of 25 volts is applied, determine the instantaneous current after 0.25 seconds, voltage developed across the resistor after 2.5 seconds, energy stored in the magnetic field, and the initial rate of current charge. Now, we know that before you can start your calculation, the first thing that you must do is to calculate your time constant. And in this case, for an RL circuit, your time constant will be given by L over R, which is 1.5 divided by 3. This, when you punch in your calculator, should give you, remember, the first thing that you need to do when you enter the exam room is to reset your calculator to its original state. Now, this should give you 0.5 seconds. This is 0.5 seconds. And then now we can begin calculating the first question. They want us to calculate the instantaneous current after 0.25 seconds. The instantaneous current in this case, I, would be given by Is into 1 minus e to the power negative t over time constant. What is the supply voltage in this case? The voltage that is supplied to this circuit, Is, which means that Is or Im can be calculated by V over R, V being 25, R being 3. You punch that in your calculator, 25 divided by 3, this should give you 8.333 amperes. So this is 8.333 amperes. Take that, you come and substitute it here. 8.333 into 1 minus e to the power, we've already been given the instantaneous time, which is negative 0.25 divided by the time constant that we had already calculated, 0.5. Now, you need to punch that in your calculator very carefully. 8.333 into 1 minus e to the power, that's a fraction, negative 0.25 divided by 0.5. Be careful here. When you press your arrow to move forward, you must press it 2 times so that the cursor becomes big than small. See, if you press it 1 time, see after the 0.5, if you press it once, you can see where the cursor is, where that flicking cursor is. That is a small cursor. If you put a close bracket there, you're not going to get the correct answer. You must press it twice. So after pressing my 5, I need to press my cursor twice so that the cursor now is lowered and it's big and visible. Then I close my bracket. I'm saying this because I've seen quite a number of times students making the same mistakes when it comes to the calculator operations. And you'd find that the student had written everything correctly, but the calculation was now incorrect because of the positioning of the cursor, which at the end of the day would result into the student getting the incorrect answers. Here we're going to have 3.279 amperes. That is 3.279 amps. That is the instantaneous current at 0.25. Now, the second question wants us to calculate the voltage across the resistor after 2.5 seconds. The voltage across the resistor after 2.5 seconds with the equation VR is equal to V supply into 1 minus E to the power negative T time constant, just like that. Now we already have the supply voltage, which is 25, 1 minus E. We already have the instantaneous time, which is 2.5. We do have the time constant, which is 0.5. Again, when you punch that in your calculator, you must be very careful. Now, I use this E here. I pressed Shift and then E because it already has an exponent. However, one may also choose to use alpha and use the E that is down there. But then that means you're going to have to bring in your exponent. But remember, the exponent there is a fraction, so you must press the fraction sign, negative 2.5 divided by 0.5. Remember about the cursor, it must be big enough. There, you get that the voltage will be 24.832. So this is 24.832 volts. Just like that. We move along. Now they want us to calculate the energy stored in the magnetic field. The energy stored in the magnetic field, you can use E or you can use angular, the sign for angular. It still represents the same thing. Well, in other equations, you'd find a W. You'd find a W. But it's still more or less the same thing. Now, this would be 1 over 2 I squared L. 1 over 2 I squared L. The I should be the supply current or the maximum current. You can put an S or an M there. That would be 1.2, 8.333 squared multiplied by 1.5. Just like that. You punch that in your calculator again. This would be 1 over 2 into 8.333 squared multiplied by 1.5 Henry, just like that. And you'd find that the energy stored in the inductor would be 52.079 joules. That is 52.079 joules, right? Lastly, on this question, they want us to calculate the initial rate of the current charge. Remember, we have the original equation I is given by Is into 1 minus e to the power negative t over time constant, right? But when you want to find the initial rate, that is di over dt. di over dt, I used to say this to my students, just go straight to is over time constant. Because manipulating the equation does not have marks, it will just be a waste of your time. So just simply move immediately to that and substitute 8.333 divided by your time constant, which is 0.5. In this case, you should be able to find 8.333 divided by 0.5. This should give you 16.666. That is 16.666. The initial rate of charging. The initial rate of charging. Now, this is the initial rate of charging. Amperes per second. This is actually the correct SI unit, right? It means that for every second the inductor is connected to the power supply, 16.666 amperes is being drawn into the inductor. Thank you very much, folks, for joining in for this lovely session. I hope it was informative and that it added a fun element to your studying adventure. Let us meet again next time for another exciting session of Industrial Electronics N6.